Okay, so I'm just gonna make up a polynomial. My goal is to do 2 of these, and then we'll see how well you can do. I'm gonna go through this really fast. So if you're getting lost, raise your hand, get some questions out there. So here's the first one I want to talk about. So function x equals x cubed. Let's go minus. Let's go 4x squared minus. Let's go. Let's go 4x minus or plus 16. Let's see, will that work? Yeah, we'll do that. Okay, so here's the problem I'd like you to write down. We're going to go through this. Hopefully I wrote that problem down correctly. And what we're going to try to do is we're going to try to draw this polynomial, right? We have select rules that we do. So the rules that we talked about in class was that there's this thing called end behavior where tails go. Because this polynomial, it's power of 3, so it's curved, we know that. And we're going to try to look at the different parts. So I'm going to just list off the things we need to know. So number 1, we need to know a leading coefficient test. Okay, leading coefficient test. That leads us to end behavior. End behavior is where the tails go, so that's a different test. So these two, they go really hand in hand. When you see them in the textbook, they list like, use leading coefficient test to find end behavior. It's like, they just know the two go hand in hand. We'll talk about those one more time. The third one is where we go after the x-intercepts. And this one is by far the most challenging. Like I'm only giving you very select problems today where you can actually factor things. So I kind of picked and choose which problems I wanted out of the book because there was a billion different problems. You guys know that they go through like 200 problems each section. I handpicked 12 that I wanted because number one, they were factorable and they were kind of easy to look at. Well, with x-intercepts, there's so many different rules to find an x-intercept. One of the rules that you can do is just set up a table where you set up x's and you set up y's and you plug in a bunch of numbers, and what you're looking for is where did it go from like a negative number to a positive number, like that, because it had to cross the x-axis. That's called the intermediate value theorem, where you're looking at just like in here it had to hit the x-axis because there was some negative number between -1 and -2, so -1.5. where it hit 0 on the x or on the y. It hit 0 up and down. Because you can see I went from negative to positive. So it had to cross the x-axis somewhere. So that's a table. I wouldn't want to do that. That takes forever. Number 2, this is the way I've kind of hand-chose problems. I want to factor things apart. There is 5 types of factoring. Okay, grouping, common factors, trinomial, difference of squares, cube rule. 5 types of factoring. This problem, I think we'll have grouping first, it'll have common factors, and it should have a difference of squares, potentially. Hopefully I worked on the problem correctly. But again, these two are like the first ones I always list. Third type, if you're not going to factor, maybe it's a quadratic problem, so you can do the quadratic formula. Now these are obviously the examples I picked are a lot bigger than quadratic, so you can't use the quadratic formula. If you don't know the quadratic formula is the -b plus or minus square root thing. You guys know the little song and dance number 4. And then the fourth one, this is the one that we're going to see in the later sections, not today. Like, it's stuff that from the questions I had on Friday, you've seen before, but I don't want to throw it at you now. It's just too long of a process. It's called the rational root theorem. And the rational root theorem is where you pick certain x numbers you want to check to see if that's an x-intercept, and then you divide them out using long division or synthetic division. Synthetic division is that one where you put a little number up in the little box and you have like the leading numbers going across and a little line underneath it. You drop, you add, you drop, you add, that type of thing. And the idea is that this takes forever because you're literally guessing and checking numbers that could potentially work. So we're going to see that in the later sections. I don't want to do it now. This stuff is hard enough as it is, let alone doing 10 hours of work trying to figure out one x-intercept. You can easily just factor it. So these are the 4 go-tos. Now there's always just guess and check, but that just comes down to tables again. So that's the x-intercept. Now one of the rules, I don't know if I talked about, I don't even know if I got to it Friday, bless you, but I don't know if I talked about it on Friday, it was called a multiplicity test. I don't know if I did that with you guys. Multiplicity test is one of the things you use with the x-intercepts. So it's always my next check. So multiplicity test. It's where you're trying to figure out, did it actually go through the x-axis or did it just bounce off of that number? And it comes down to when you factor it, what does it look like? So we're going to hopefully take a look at one of those. And then the last 2 rules is you have y-intercepts. That's one of the easiest things to do. You just plug in zeros. And last part is symmetry. This is a part that I know for sure that we talked about, but we didn't go in depth. I didn't have you try one. I just kind of showed you what we're going to do. So symmetry, and that leads you to one of the new parts that we have not discussed yet, which is called turning points. The turning point, I guess, check or test or whatever it is. So these are your kind of 7 major bullets that we talk about, the 7 checklists that I go through when I'm graphing this thing. Now, obviously people could just type this in like Desmos and kind of see where it goes. But like when you're on an ACT, when you're on a math placement test, if you're on a maps test, they don't give you, Desmos to work with. Like you guys, when you did maps, right? They give you this simple, stupid calculator up in the corner that you can't even do trig functions on, right? It just adds, subtracts, multiplies, and divides. Well, if they ask you to evaluate a problem like this, or like see what happens when you go up to the number 10 or beyond that, knowing how to graph this thing is actually really helpful. And these checks are really quick. The only one that actually takes work is the x-intercept one, because that's one where you have to factor and you have to pull things apart. So it's one of those things like, it's something that when I look at a problem, I can just instantly kind of see where it's going. I don't know the exact x-intercepts, but I know like generically what it's looking like. And that's one of the things you just need to see. So let's go through the list here. Hopefully we can get through this one and the next one. I want to try to go through 2 of these really fast. I'm not going to take as much time as like I did on last Friday. So first step, leading coefficients. What's the biggest power on this problem? 3. Okay, we're looking at this item. It's a 1x to the 3. So there's 2 checks I do. I do the leading coefficient test, and then I do the end behavior test. I do them all at once. So the leading coefficient is the number out front. Since that is positive, this thing is going the normal route. This is a normal graph. I know that doesn't mean much for you right now if you don't know what that means. This graph is going to be facing the normal direction that an x cubed graph would go. X cubed, which you're going to see in this next test, which is end behavior, faces a certain direction on the right side, faces a certain direction on the left side. Well, this is telling me, since this is a positive number, it's going the normal directions. If this was negative, it would be a total reflection. We'd flip the graph over, and I'll show you that example here in a second. But the next test, which is end behavior, so this is a normal graph, this is the positive number. The next test is the power. So I look at the power, since this is an odd power, that means the tails for end behavior, tails go different directions, which is normal for a cube graph. So anything that has an odd power on it, like 3, 5, 7s, 9s, those will go opposite directions. So the tail, one tail goes up, one tail goes down like this on the outsides. This is what I'm looking at. That's a normal x cube graph. What we're going to try to figure out is the middle ground. Does that make sense? Okay. Cubes or fifths or sevenths and odd powers go opposite directions. Because as you plug in positive numbers, they stay positive. You plug in negatives, they stay negative. So that's why they face different directions. If this was a negative number, like a negative 1, then what I say is that instead of a normal graph, it will be the opposite graph. So the graph would be going up here, down over here. That's how I know. Like I can just instantly tell that. Questions about the first 2 tests? I said they're quick. Perfect. Let's go through the next one. Okay, next check, we have to do the factoring idea. We have to do x-intercepts. So I'm going to write this problem over here. Now, this is a cube root function. It's not a trinomial or anything like that, so we're gonna have to do grouping method. There's actually 4 terms here. So to group, what do these two have in common?
X squared.
X squared. So if we pull out an x squared, we're left with an x minus 4. Perfect, okay? In the back, I'm gonna, back here, it looks like they have a 4 in common. I'm actually gonna pull out a negative 4. You'll see why here in a second. So if I pull out a negative 4, we're gonna divide both items by negative 4. I get an x, because negative 4 divided by negative 4 is 1. And 16 divided by negative 4 is negative 4. So I divided the negative 4 out of that thing. Both items divided by negative 4. Now, why did I do that?
So match.
Yeah, exactly. The parentheses match. Parentheses look the same now. So that's something you just got used to. Sometimes it doesn't work out. So that's something I was kind of worried about when I just made up that problem. Now, going through now, I'm going to pull out what these two things have in common. Well, they have the x minus 4 in common. So I'm going to pull that out back. I'm pulling both of these out back. But you only put one of them because you're pulling out the common thing that they both share. Okay, are we done yet? No. What do I have left? Yeah, difference of squares. So this item can be broken up into 2 parentheses. This one in the back doesn't, that's not a difference of squares, but this one is, it's plus minus, it's gonna be x and x, 2 and 2. So, as you can tell, we have 3 x-intercepts, because what was the biggest power on this problem? 3. It potentially, notice that word, has 3 x-intercepts. 3 numbers where they match, because of the power. If this was a 4th root problem, it would potentially have 4 x-intercepts. But this has 3. It doesn't have to, mind you. It could just cross once. Because maybe this thing went up too high. Because I had a plus 16 on this thing, so maybe it shifted up way too high. So it only hits the x-axis once. That type of thing works over here somewhere. But this one has 3 because we actually factored it apart. And what are the roots? What makes that thing a 0? -2, 2, and 4. Okay, those are my x-intercepts. They're called x-intercepts, or roots, or they're called zeros. They all have the same name, and the reason why they're called zeros, it's the numbers that make them 0. That's why they're called zeros. So, those are my 3 numbers. So -2, 2, and 4. Boom. So we're actually hitting 3 times. Now, notice those 3 dots I've just drawn. Right now, I can already tell you, by seeing those 3 dots, those 3 x-intercepts, I can already tell you about that test, the symmetry test, the one we're going to see later. This thing is not symmetric. Symmetric is like when pictures look perfectly balanced, right and left side. Can you tell that the left side and the right side are not the same? They're not hitting the same x-intercepts. So it's not symmetric. I can already tell you that. But we have a test for that later, so you can see that. Okay, is there any questions with the top 3 checks? The x-intercept stuff takes the longest. You have to factor it, you have to know the rules, factoring it completely as far as you can. And sometimes it doesn't work out, so you have to kind of, maybe there's only one. I'll show you a different problem after this one. Okay. All right, multiplicity test. We have to go after the parentheses I just used. So what we have to look at now for the multiplicity test is what are the powers on these parentheses? Like what's the power on this parenthesis right here? 1. Power on this one? 1 and 1. Since they only have 1s, that means I'm passing through those x-intercepts. It's going to pass through. That's what the multiplicity test is. If they're odd numbers for the powers, like maybe there's a 1, a 3, a 5, that type of thing, you're going to pass through these numbers. That type of thing. And that kind of follows, like if I'm kind of like guessing where these things are going, and I'm passing through them, it does make sense where the tails are finishing, since I'm ending up going to the up on the right side. So passing through them actually made sense. If these were even numbers, which you're going to see in my next example I'm going to make up, if these are evens, I'm going to bounce off of them. I'm literally going to bounce, so it'll like come down and touch that number, and then turn around without going on the other half of the x-intercept, or the x-axis, I should say. So we'll see that in the next one. But that multiplicity test goes after the x-intercepts. Okay, does the odd numbers make sense, like the powers? I'll show you a different one. We'll change it up here in a second. Okay, y-intercepts. The y-intercept is one of the easiest checks in the world that we do. You plug in the zeros. Oop, I just erased something I shouldn't have erased. Okay, plug in a bunch of zeros. What do we get?
16.
Yeah, 0, 0, 0 plus 16. Yeah, you get 16. That's your y-intercept. So this thing is hitting really high on the y-axis. Again, I didn't know where these peaks and valleys are, so that makes sense. It's going way up here and going way back down. Because again, I don't know the peaks and valleys. I have no idea where they're going to be. I just know where the x-intercepts are, where the y-intercept is. I know where the tails are finishing. I don't know the little details in the middle. Like especially like right here, at this spot, I have no idea how deep that thing goes. I have a test I can do to tell me where it goes, but I don't want to show you that yet. Maybe I'll show you that later on this week. Okay, questions at all about my rules so far? Okay, so we're through the first. Now, symmetry. This thing is not symmetric. I already kind of warned you of that. It's definitely not balanced. You can see it from the 3 green dots. It's not perfectly balanced over the y-axis. There's 2 types of symmetry, if it's symmetric at all. And the types of symmetry are called even and odd. An even symmetric graph looks like this, where whatever it's doing over here, it's going to do the same thing on the other side. That's an even symmetry problem. It's like perfectly balanced right and left. Odd symmetry is when they do something like this, but then it does the complete opposite on the other side. So instead of, this side went down, this side went up instead. That's an odd symmetry. So they look the same, but it's going the opposite direction. Usually on odd symmetry, and this is something that you just need to know, they have to be perfectly balanced over the origin. That's for odd symmetry. That's something you need to know. It has to go through the origin, 0, to be odd symmetric. So that would have to be one of your x-intercepts. That's kind of like a red flag in my mind, because they have to be balanced. Now, your problem, I already kind of warned you, yours is not symmetric. How I know that? There's a test we do for symmetry. How do you know which type it is, if it's symmetric at all? You do this. You take your function, this is my function here, and what you do is you plug in a negative x into it. And all you do is you simplify the problem down. So, negative x to the third, negative x squared, negative x times negative 4, and then a positive 16, right? Because you only plug negative x's where there's x is located. And what you do is you do that little common sense rule, where if it's an odd power, it keeps a negative. If it's an even power, it cancels the negative sign. So this is an odd power, so it keeps the negative. That's an even power, so it cancels this negative sign, like that. So it just cancels it out. This is an odd power because it's a 1, so the negative sign will come to the outside. So double negative made positive. And then the positive 16 didn't change. Now, when you look at this, after we simplified it using common sense, is that the original thing we started with? No, it's definitely not. Is it the exact opposite of what we started with? No. So this is not symmetric at all. It's neither. What I mean by exact opposite, if I want this thing to be an odd symmetry graph, everything would have to be the exact opposite like this. And there was no way to change the 16. So the other way that, I think the other common sense way, I think I explained it last Friday, for symmetry, for odd and even, if you're going to have symmetry at all, you look at the powers on all these items, and this one's by far, this one's an x to the 0. Are all the powers even numbers? No, they're not. It's a mixed bag, right? It's odds and evens, so it's not symmetric. If they're all even numbers, it's probably even symmetry. If they're all odd powers, then it would be odd symmetric. That's like the 2-second check that you can do in your head. The book says you have to do this. Just look at the powers. It's a mixed bag of evens and odds, so it's not symmetric. I consider 0 to be even, by the way, if you're doing the even odd thing. So it's not symmetric. And again, the green dots already told me that in the very beginning. Now, turning points. This is something brand new. We've never talked about turning point tests. The turning point test is to figure out how many times this thing turns directions. We've never discussed this. This is something that I didn't even do last Friday. So the turning point test is where you look at your problem and you take the highest degree. So the highest degree term is x to the third, right? That's your highest degree. I'm looking at the power, the 3. Okay. What the rule is, what you do is you take the highest power, you subtract 1 off of it. So this turns out to be a 2. This number that we just made up, is how many points, or how many times I should say, this graph will turn directions from its original path. It should turn twice, 2 times, as you flow from the left side to the right side. So what I mean by that, this graph started down here, right? That's where I said it was going. So as it continues, so I don't know where the arrow is. I think the arrow is generally this direction. It's going something like this. That's what I'm thinking, because it's going down. So as I'm going, it should change directions once to go down the opposite direction, like change slope basically. So it changed, and then it changed again. So it had 1, 2, and what should happen here is it should end up going that direction, which makes sense to everything I've said so far. So does that make sense that it turned direction twice? Now, that's a potential. It's like the x-intercept. It has potential to have 3, it doesn't have to. Because on some of these problems like this, it could just do something like this, where the graph goes up and just kind of levels and then keeps going. It doesn't have to do that weird squiggle where it goes down and back up. It doesn't have to do this radical like change. It could just be a slight change. How I know if it's going to be this radical like switch, like what I'm drawing here on my original picture, how do I know it's going to do that? Well, it's how many x-intercepts it has. That kind of tells me. And number 2, how many letters do you have? Are all the variables accounted for? It has an x cubed, x squared, an x, and a 16. If all the letters are accounted for, it's doing what you see here on the board. It's doing that radical thing where it's changing directions really, really hard. If it's missing a couple letters, it's doing the thing where it smooths out, where it doesn't like radically like dip up and down very hard. That's just something you get used to when you start to see many, many examples. Okay, questions at all about these problems? Okay, I know that was kind of like the 10-minute check on that one. I would not take 10 minutes. I can usually do one of these problems in a minute or 2, just because of the x-intercept slow me down, the factor. Okay, are we good so far? Okay, last example today. No joke, last one. I want to do one more. And I want to see how well you can, how well you guys can do. Okay, all right. Next problem. So my last example, then I'm going to have you guys try one out, and you guys have to walk through it together on the board. You guys going to help each other out. Okay, this next one is going to have a radical change in it. I'm going to give you a completely different look to this problem. So, let's go 3. We're going to go x plus 1, x plus 1, x minus 4, x plus 5. Now, when you look at this problem, you're looking and going, okay, this is kind of weird. Why is it written like that? They don't have to write it as a full-on polynomial. They could already have it factored for you. Here's the best news. When you look at that problem, they already gave you your x-intercepts. Those are awesome. So we already know the x-intercepts. The only problem is we don't know the original polynomial. So I don't know where the end behavior is yet. I don't know where the leading coefficient's going. That's something I'll show you my little shortcuts for doing that. I can do the multiplicity test really easily here in a second. Y-intercepts will have to actually do some actual work. It's not as simple as like what we did earlier. Symmetry is pretty easy once you look at your x-intercepts, and then the turning point's pretty easy once you know the shortcut for doing the top 2. Okay, does this make sense? Like it's a completely different look to the problem? Okay, so now, when we're at this problem, let's do the first test, the leading coefficient test and the end behavior. Where is this thing going? Okay, what I do, this is kind of goofy. I'm going to look at all the numbers out front of all these x's. So what are all the numbers out front? They're all 1s. But then eventually, if I were to like FOIL this whole thing out, I'm not going to do that. But if I were to FOIL this whole thing out, it'd be 1 times 1 times 1 times 1, which would be 1x to the 4th. And then we would take it times the number out front, which would make it 3x to the 4th. Does that make sense? Without having to do any work. That's what the first term should be in the long run. It should be in 3x to the 4th. So now that I know that, just common sense, multiplying the first terms together plus the numbers that were out front. Where are the tails going? What's the end behavior look like?
Opposite. Normal.
It's a normal graph because the positive number out front, okay? So this, since this is a
That's
positive
normal.
3, this is a normal graph. Now here's the problem. We know it's normal because it's positive, but where are the tails going?
The same
Up
way.
and up.
Yeah, they're going the same direction, they're both going up. The reason why they're going the same direction, it's a power of 4, it's even, so the tails don't go different directions, they go the same direction, they're going up. This is where my thing is going. The outside tails are going up. I have no idea about the middle ground, but the tail's going up. Make sense so far? Okay, that's doing the little simple check with the even power, the positive number up front. X-intercepts, what are my x-intercepts on this graph?
-1,
Okay.
4, and -5.
Boom. There's really only 3. Even though there's listed 4, one of them repeated. So -1, 4, and -5. 1, 2, 3, 4, 5. Okay. So we have only 3 x-intercepts. Even though it was a power 4, I said potentially there's 4 x-intercepts, but one of them repeated. So we figured out. So now, is this thing symmetric or not symmetric? It's not. You can see the x-intercepts. This thing is not symmetric. So I already know right here on the symmetry test, the x-intercepts are telling me it's not symmetric. So we already know that. So it's not perfectly balanced. And that helps you if, like, you know it's symmetric, you can make the pictures look the same on both sides. That's why it's useful. All right, now we have to do the multiplicity test. So now we know the tail's going up and all that good stuff. We have to check, is it passing through the number or bouncing? What is it doing? Okay, so on this one, I'm going to combine these 2 parentheses down into 1 parenthesis. They're both the same, and there's 2 of them. That helps me with the multiplicity test. So now, here's where we're at. So, since these powers are odd numbers, we're going to pass through these x-intercepts because they have an odd power on them. And this one, since it has an even power, we're going to bounce off of this x-intercept. It'll bounce off of it. So it'll hit that number and then turn around and go the same direction it was going. So let's actually draw this. So we're going to pass through -5. So let me try to roughly draw this. So I have kind of a rough scale of what's going on here. So we're passing through -5. It's going to somehow turn around. I don't know where it's going to turn around. We can see that later this week. It's going to turn around and bounce off of -1 because it had the multiplicity test had it as a 2. It's going to bounce off of that number. And then eventually it's going to go up and it's going to pass through +4. And that makes a lot of sense with where the actual lines are going, like the tails are finishing. So that makes total sense now, why it's doing that. Okay, now, the only thing that I probably need to change here is the y-intercept. I don't have that yet. Because I did the multiplicity test and I kind of did a rough sketch there, but I forgot to check the y-intercept first. Now this one is not as easy as the last one, that you can't just plug in, and see instantly what your answer is. Some people, like on that last one, they just know it's 16, it's the number in the back. This one, I don't know it. So you have to actually plug in zeros and actually figure it out. So this one is actually the one where y-intercepts take the longest, because you have to plug in all the zeros into everything with this. So that's 5 times -4 times 1 times 1 times 3. So that's -20 times 1 times 1 times 3. So this turns out to be a -60. Yikes. And that makes sense for where we're at. So my drawing is a little bit off, just a hair. It's more like something like this. So it bounced, and my goodness, it went way down here and then came back up. And this was -60 down. As I can tell you, it's really tough. And I don't even know if it turned around at -60. That's where I know it passed through. Because it could have went, it could hit -60 and then just kept going for a while and then turn around. But figuring out those turning points, that's what we do later on. Maybe we'll try it this week. I'll show you kind of the idea. All right, so I think we have most of the sketch done. We know it's not symmetric. How many times should it turn directions? 3, because it was a power 4, right? This is a 4th term polynomial, so it should turn 3 times. So from its original path, so it was going down originally, switch once, switch twice, switch 3 times. So yeah, so the turning points were correct. So it should have potentially did 3. Again, it doesn't have to do 3. It really depends if it had all the variables accounted for. So if you actually FOIL this whole thing out, you can tell like if any of the letters were canceled, it'd be more smooth. It wouldn't be so jerky up and down so much.